Hello everyone. Today we are here to talk about cloning. Dolly the sheep. We all know famous Dolly the sheep, but before we actually saw the living, breathing proof of concept, most people even didn't know that it is possible. And then they cloned a cat. They actually called it copycat, or CC, then a horse, and nowadays, if your pet that you really loved just died, and you have a spare $100,000, you can have it back again. But why don't we clone humans? Well, there are several reasons for that. For example, one of them is commercial. At least there is officially no commercial interest in cloning humans. Of course, there are legal and ethical issues, and most of all, most scientists agree that it's really difficult to clone a primate. For the pets, it's easy, but it's really difficult for the humans. But can we be really sure that there is no living, breathing human clone around us? And how about mobile contactless payments? Based solely on the market growth prediction, I think we can safely agree that fraudsters have commercial reasons to do it. And of course, stealing is illegal and unethical, but I don't think fraudsters have such kind of morality. So the only safeguard we have are the technical countermeasures, and fortunately we have a lot of them. There is tokenization, provisioning, and so on. We have a lot of countermeasures, but can we be really sure that they can withstand the incoming threat? We will find out in a few minutes, but first we need a short introduction on this technology. Host Card Emulation. Anybody pays using the phone? Contactless payment? Anybody? Okay, great. Some people. Anybody is implementing it, for example, from a bank or, oh, yeah, there is someone. Let's get back about 10 years past, where the first mobile contactless payments were born. The idea was to make it as secure as the plastic card. So there was this secure element hardware, and in this hardware, all the keys and encryption they needed for encryption were stored in process in this secure element hardware. And the mobile application, mobile OS, didn't have access to this. But that required cooperation with mobile operators and banks, and everybody wanted to have control over it, and it was really difficult to agree, and it's quite a painful process from user perspective because you needed special SIM and so on. So when in 2011, when the Google announced the first mobile wallet, Google Wallet, it was based on Galaxy Nexus secure element in the Google's own phone. The mobile operators have their own vision how to rule the world. They created ISIS. Actually, yes, it was called ISIS. And they deliberately blocked Google Wallet on their own devices because Google wanted to use the secure element. Google, well, of course, a few years later they had to change its name, and then Google bought what's left of them. But actually, in the meantime, they started another revolution, which couldn't be stopped later. They created so-called host card emulation. So the secure element was moved to the cloud. And everyone is happy because there is no need for a very difficult agreement with the mobile operator. And the secure element is in the cloud, and everything is in software. How does it work? Well, I will try to show it to you I have the mobile contactless payment terminal. Hopefully I will be able to make it work. Yeah. So there is a phone. I just put the phone over there, over this terminal. Maybe it doesn't work because of the rubber. Okay. So it's confirmed. I just put the phone close to the terminal. I don't need to do anything. I don't need to unlock this phone even, and it just works. Oh. So it was visible only on my screen. Sorry for that. So let's do it again. Okay. Okay. Nobody told me that you don't see it. Okay, so we'll make it another one. I just put it close. Okay, and it's confirmed. I just put it close to the phone, and it works. So let's get back to the slides. Okay. But if you are a bank and you want to integrate it in your mobile application, you have a few options. You can use, well, you can write it by your own, but it's very difficult. But in most cases, you take external library. There are SDKs from Visa and MasterCard, but there are other several commercial products. And the documentation of this looks like this. The keys are secured in secure environment, guarded by 2 firewalls and reverse proxy. This library is called HCE applet, so they use exactly the same name as for secure element Java card applet, and they try to picture it as an external entity, and the only thing that the mobile banking developer is interested in is SDK. He doesn't know how this works. So as for us, it was quite obvious that you can just copy this data, because this data is in mobile applications folder. It's just a library. That was somewhere lost in translation, that it is possible to clone. So we noticed that our clients could not believe that it's possible to technically do the cloning. So we decided to make proof of concept. And that is where my research starts. My name is Sławomir Jasek, by the way. I work for Securing. We spent a lot of time for research. And of course, we are hiring, so if you want to work, come to visit our booth over there and talk to us. Okay, so let's cut to the chase. How do we steal the money? So I would like you to try to imagine that you are a group of thieves, and there is a new lucrative target, money in the phone. So in this phone, there is money. You just put it close to the terminal, and you can pay using it. So what would you do as a thief? Well, you could just steal the phone, right? So you could make transactions using this phone. But think of it. If you would lose your smartphone, exactly how many seconds later you would know that you don't have your smartphone? Of course, you would immediately report it to the bank as soon as you will find a way to contact your bank without your smartphone, but that's another problem. And I don't think it's a real risk. And based on the statistics of real plastic cards stealing, well, it's not really a risk. So maybe we could steal this data somehow using NFC reader, for example. There are applications called NFC reader, so we could just read this card number. I can show it to you also. So I have this NFC reader. So when I press it close, oh, sorry again. Okay. So this is NFC card reader. So when I press it close to this phone, I should read. Well, it doesn't work. Well, it turns out that I need to turn the screen on in order to read it. So now I can read it, and you have the card number over there. So how many of you already scanned this card number? It turns out that even if you did, you wouldn't be able to use it for payment because the screen has to be on, so this attack is not really easy to do because without user interaction via Pocket or something. And you won't make online payments using this card number because this is not the original card number. This one is so-called tokenized one. So maybe you could do Magstripe track 2 and use it in a terminal that can is backwards compatible via NFC, but I don't think you will be able to do it. If you do, just let me know so we can talk about research together. But I don't think you would be able to use this NFC sniffed data to anything because of the so-called tokenization. So your real card number is changed to a random one. And this random card number has limited domain use, so you can't use it in online payments. It's just used for the NFC contactless payments and for the terminal to know which card it speaks to. So how are these NFC transactions actually executed? Well, you need to have not just the card number, but the key which encrypts the EMV communication with the reader. So this is the key that a thief would be after in order to make mobile contactless payments on another device, for example. So how can we steal this key? Well, maybe we could intercept it in transfer. It has to be somehow transferred to this device, but this infrastructure is quite complicated usually. It involves communications with many servers, and usually it's quite well secured. So there is, of course, certificate pinning. They use second layer encryption, so you don't see just the clear text communication. It's somehow encrypted, besides, of course, TLS. So there are possible flaws in it, problems with certificate pinning. I could talk hours about the deeply hidden bugs under this proprietary encryption, but it's as it is very interesting for pentester, the real risk is I don't think it's possible to really exploit it. So I don't think it's possible to intercept this in transfer. So any other ideas? The key is just stored in user space. There is no hardware secure element. So maybe we could get it somehow from the phone, and for that we could, for example, use mobile malware. The most common mobile malware nowadays is just a malware that presents overlays over users API GUI, and can intercept text messages and intercept pins and so on. But this kind of malware doesn't have access to the private folder of the application where the card data is stored. So in order to access this private card data, we need special rights. We need to have root. And root is the god. It has access to all the data without any restrictions. So having root, we can get access to this data. In order to have the root, we could have a malware which infects the mobile phone and then exploits vulnerabilities in it in order to gain these root credentials. For example, you have an not updated Android phone. It's not very rare. And it has some vulnerabilities in it, so mobile malware can exploit them to gain root credentials. We are not talking about users rooting their phones. We are talking about malware which can get root credentials without the user knowing it. And there is recently there is a lot of such malware which infected millions of devices. And so this risk is real. So if we would have the root malware and remote access to this phone, we could get this key. But this key is encrypted. Well, we could expect it somehow. Of course, they encrypt this data. They try to protect it from the thieves. So what can we do to retrieve this key, to decrypt it? Well, this is Android application, so we could try to decompile the binary and get the source code and understand how this encryption works. But it turns out they use obfuscation. So it's quite difficult to understand this decompiled code. It may be possible if you spend a lot of time on it, but you would, and as an attacker, you would need to do it for every application because they are differently encoded. So I noticed that most creators of such security mechanism, they tend to imagine that the attacker will take this simple tool and try to attack this security mechanism just by using the simple tool, and he will fail, of course. But what if there was a workaround just around these security mechanisms? So if you take 2 steps back and think how this encryption works, it doesn't require any user PIN or password entered on the phone. And there is also a business requirement that it has to work offline. So if you don't have internet connection, you also have to be able to make the payment. So how the key is stored? Well, the key has to be stored also somewhere on the phone, or maybe it can be hard-coded in the application binary, right? There is just no other way to do it. So what can we do to clone this card? You probably have an idea. So we could just take another device and install exactly the same application and copy all the user's data. So it should just decrypt itself, right? So let's try to do it with Android Pay. So I just showed you Android Pay working on this one. So I will connect to this device. Okay. Oh. I will connect using ADB, but let's imagine that I have a malware with remote root access to it. So I will get the shell on it. I will use my secret access to the root and invoke the backup script. Okay, so now I'm just getting all the data. Yep. Okay, so we have the data. Now I will just download this data to my computer. Remotely. And then I will have another phone. This one also has Android Pay installed, but it's not activated. So, of course, this is the attacker's phone, this one, the black one. And when I run the Android Pay, it just needs to be activated. So it doesn't work yet. But I will connect to it remotely. I just need my show. OK. I will connect to this other phone. OK. I will push this cloned data to my attacker's phone. Wi-Fi is a bit crowded there. OK, so it's already on this attacker's phone. I will just get the shell to it and my secret super user, and I will just restore this data. And can restore message. Oh. OK, so now I'm restoring it on this device, on my attacker's device, and I will just reboot this device to get all the settings correctly. Let's do the camera. Oh, yeah. So it reboots now, and in a few moments it should have the cloned data. So I will try to make the payment again. OK. So let's try to make the payment using this cloned. Oh. OK. OK. Oh, it requires me to put the card in, but I'm not able to do it. Let's do it again. It's not because of the cloning failure, it's because the failure in communication with the payment terminal. I can already scan this using. Let's try again. Using card reader. So when I put the card reader to this cloned phone, pin required. Oh, OK. So now I have exactly the same card number on this cloned device. The only thing left is to make a transaction, and so let's try to do it again of this terminal. OK. Please wait. And it is confirmed. So I made the So I was able to make the transactions using this attacker's phone. Copied this data from this one. So let's get back to the presentation. And you probably want to know what was in this cloning script, but it wasn't rocket surgery. I just used 3 commands that you should know. It was tar to copy the data, change owner when I was restoring it, and also restore con, which helped me to restore SLinux privileges. And I actually promised not to disclose these scripts, but I think you deserve for them, so I will show them for just a few seconds. Are you ready? Oh, you had your chances, right? And the restore script. There it was. So this worked for Android Pay because Android Pay just checks device ID. I also copied by copying data. They check Android ID, not device ID. But most other banking applications, when you try this trick, it doesn't work. Why? Well, because the encryption key is tied to the specific device. Besides there is some key element stored on the phone and hard-coded in the mobile application, they also check device-specific characteristics. So if you just take it and copy to another device, it doesn't work. So what if we took exactly the same phone, the same phone model, and we also cloned the IMEI number, so they are physically the same. So it turns out that it works. And in most cases, you need to copy also other user data, not just from this payment application. But this is not really practical attack on a mass scale. So if an attacker would need to buy exactly the same hardware phone, the return of investment wouldn't be really interesting for the attacker. So what can we do to make it to a different device? So we can use so-called Xposed Framework, which intercepts the system calls and can spoof the device characteristics. So on a standard device, when the mobile application asks for device characteristics, it just gets them straight from the OS. And if you have this Xposed Framework and install special module for changing device ID, it is intercepted and you can return anything. So we can spoof the device characteristics on another device. And it looks, from the mobile application point of view, it looks exactly the same. So we don't have this, we can work around this security mechanism. So we made a single transaction for 1 Polish zloty. And well, it shouldn't be a problem because the payment keys that are stored on this phone, they are limited use. So you can just make a single transaction or a few of them, then you have to refresh these keys. And of course, the transactions for higher amounts needs to be authorized by PIN. So let's take a look at this key replenish process. How do you get more keys on this device after you use this single-use keys? Well, it's usually quite complicated process, also involving a few servers. In most cases, let's say that part of the key is taken from the mobile wallet server, and another one is pushed through Google Cloud Messaging. So you have to intercept both of them. And this part is we actually already done because we spoofed the original device, and when we talk to the mobile wallet server, it just can't tell which device it's speaking to. So we can imitate the original device in the request to the server and get the exact same responses. So the only thing left, we need just to hijack the push, the Google Cloud push, which goes to the original device. And If we still have access to this original device, we could just intercept it on it, but it would be more interesting to reroute it to our device. So I made an experiment that I cloned all the user's data, including the data needed for Google identification. And in this case, both devices have the same Android ID, keys, and Google subscriptions. So I was able to get the Google push from the cloud on the cloned device. And in this case, intercept this data. So I can make multiple transactions. I can renew these keys. So, well, we have, of course, we have limits on the number of transactions, and the thief would be rather after one single transaction on a large amount, not multiple small amount transactions, because that would be much more difficult to steal and easier to catch the thief. So, fortunately, transactions for over 50 Polish zloty needs to be authorized by PIN, and you enter this PIN on a terminal, right? So this is called the floor limit. And you should enter this PIN on a terminal, but how do you set up this PIN? Well, it turns out that in most mobile applications, as a business requirement, you need to, the whole enrollment process needs to go through mobile. So when you enroll for a new card, you set up everything in your mobile phone, including the PIN. So you also enter this PIN on your mobile phone. So if I have access to this phone, I could intercept it, and I could trick the user into entering it later, make an overlay or something, and the user will probably enter this PIN to my malware. And there is also another very interesting feature. It's called CDCVM. So this will be the transaction over this floor limit, and just pay attention where do you enter the PIN. So you authorize these transactions not at a terminal, but on your mobile phone. It's called consumer device cardholder verification method. So when both devices, reader and the phone, agree that they support it, then the cardholder verification is performed on the user's device, and it doesn't ask for the PIN. The terminal doesn't ask for the PIN. So, of course, malware on this device could steal this PIN. But, well, it turns out that most applications do not have this CDCVM feature. It just enters this market, and, well, maybe 1 in 5 applications have this feature. But how about application that doesn't have this feature? Well, can we attack it? It turns out that even if application doesn't have the CDCVM feature built in, the HCE library it uses, it has this feature. So these are the method names in one of the libraries. They can't obfuscate the method names. So you can see the set CVM verified, and you can set it to true. So we could just take a mobile application and patch it to set CVM verified. And then even when the application doesn't support the CDCVM, we could just force the reader to believe that he doesn't need to ask for the PIN. So in this way, I could probably make transactions on a higher amounts, not just this few lower amounts transactions. And this is, of course, a much bigger risk. So we have tested several applications. I believe it was 9. And we have proved all of them possible to clone this card data. all these applications we can estimate based on the HCE libraries they use. We have tested 7 various libraries, so in most cases, other applications that uses the same library will work exactly the same, and we will also be able to clone it. The easiest applications didn't check multiple device characteristics. So I could just copy the data and change the model in the build prop file. There was no root detection, so I didn't need to hide it. And in order to replenish the keys, it wasn't the Google Cloud involved, so just a simple API request to the server, and I got the new keys. On the other hand, the hardest application had checked multiple device characteristics. So in order to clone the data, I needed to use Xposed module to spoof the original device. But Xposed needs root, so I needed to hide this root. But this application had a very good root detection using native library. So it was very time consuming to do it, and finally I did it using exactly the same hardware device just to make the proof of concept. But as an attacker, I would probably leave this application alone and move to another one. So what can we do to prevent it? Well, the obvious question would be, can we prevent the cloning? Well, unfortunately, at this moment, no. The best thing we can do is just don't be the last one. So you can use multiple security mechanisms to divert the attacker to another weaker application. And we can check for more device characteristics to make it more difficult to spoof the original device. We could improve the root detection. Google's safety net is quite good, and they have potential to make it better. There is open source root beer, very good. Google's safety net, well, it's not perfect at this moment, but will be better, hopefully. If you know a little bit about root and root hiding, you probably know that it's kind of cat and mouse game. So if having root, you can always hide from the root detectors. Just like I did a few moments ago for the safety net, which was used in Google's Apple Pay. This is the safety net decompiled code, which checks for super user binary. So instead of using SU, I used my own initials, SJ. So it didn't detect this phone is rooted. But they have potential to make it better and integrate better with the phone. Of course, we can improve integrity checks, binary protections, use key stores, and so on. And last but not least, we can make better fraud detection to integrate things from the phone into existing fraud management systems. For example, make device scoring that impacts the risk. If you have a really old Android phone, there is a much higher risk that your phone may be attacked by malware, for example. Well, there are malware detection systems for mobile phones that are far from perfect. So probably you should think of making something by your own. In the future, well, I'm quite sure that Google knows that with great power comes great responsibility, and they are working really hard to make the devices more secure. I hope in the near future we will have trusted execution environment and deeper integration into hardware, but well, we don't know. And on the other hand, we will have much more widespread mobile payments, and of course it will attract more attention of the fraudsters. So let's hope for the best, but I would suggest to prepare and verify for the worst. And with this hopefully optimistic accent, I don't want to be the last one standing between you and the after party. You're free to go, and if anyone has a question, you can just catch me there or near our booth over there. So thank you.